Hi and welcome everyone to our presentation of cobalt in the United States, the year of 2018. And presenting today is me, Sofia.
And me, Erik.
The aim of this study was to evaluate use and production of cobalt from a sustainability perspective. And the first objective was to identify critical flows in the system. It was also to evaluate trade availability and resource distribution, stocks, extraction limits and recycling rates, as well as historical trends. We also wanted to look at land use impact and attribution. And finally, it was to dig deeper into accumulated material and dissipation, as well as environmental impacts, ecological and human health effects. So, a bit about our material in general. It is a trace metal and is therefore only found in small amounts in the lithosphere. It is almost without exceptions a byproduct from nickel and copper mining, and the largest share of world cobalt mining is located in Congo on the African continent. After mining, it is refined to a solid metal or an oxide powder. Cobalt is used in blue pigments that you often can see as a coloring agent in ceramics. It gives also magnetism and strength to alloys at high temperatures and are therefore used in, for example, aircraft engines. Cobalt has also catalytic properties and are therefore used in different chemical processes, just to mention some examples. So, the method we used was both a literature study for our qualitative parts, but we also used statistics and reports for our more quantitative parts. The webpage of United States Geological Survey was used to a high extent, and when no real numbers were available for certain flows, we used estimations from old flows in these reports. So let's move on to the results. We're now going to bring up our material flow analysis, availability of resources, land use, and assimilation capacity for cobalt. So this is how we imagine that the system for cobalt in the US looks like. We have, as you can see, split it up in mining and enrichment as the first box, production, and then the use phase as represented in the red dashed box, including usage of 4 different product types inside. And then we also have import-export on the top of the picture and lithosphere and environment in the lower part of the picture, as well as incineration and landfill to the lower right. One thing that is especially interesting with cobalt as a material can be seen in the lower left side of the MFA, represented as a box called mining waste. This is because, as we mentioned before, cobalt is mined as a byproduct of nickel or copper, so sometimes it is not seen as economically profitable to extract the cobalt if it's mainly another metal that you are looking for. We have found that globally 25% of the mined cobalt is actually never refined but put on pile like this, but we don't have any exact numbers when it comes to the US. We have also relatively high losses in both mining and production, as you can see here as 12 and 442 tons. The arrow that goes from import to the blue dashed box show that we don't know exactly how much of the imported cobalt that goes into production and finished products respectively. The stocks in production varies from year to year, so the year of 2018 you can see that it decreased with 10 tons, which is a small amount just like the production stock in general. This is of course quite expected, since a producer of course wants to use the cobalt quite immediately in production. But the stock in use phase as finished products is obviously much larger, since many products, as for example gas turbines in airplanes, are used for many years. The flows that we weren't able to find or estimate in any way is the dissipative use that goes directly down from the red dashed box to the environment, as well as the material that goes into incineration or landfill. The waste of cobalt that is exported was not possible to quantify either. The number of 2,740 tons for scrap that we found is shown both as an arrow from the use phase to production, but also as an arrow from production and back into the same flow. This is because we know that this is a reliable statistics, but it's not stated how much comes from finished products and how much that is reused in the production step. Here we have a more detailed picture of the use phase that shows how many percentages of the US production that goes into different product types. 46% goes into superalloys, which can, for example, be used in airplanes, space vehicles, and nuclear reactors. 8% goes to cemented carbides, that mostly is used for cutting tool material. 31% is used in a different range of chemical applications as catalyst or paint, and finally 15% are used for other metallic applications, like for example electronics or other alloys that aren't superalloys.
Next, we'll look at the availability of cobalt, both from a US and from a global perspective. In the top right figure, we see that the mining production of cobalt for countries as a percentage of the total world production. To the right, we can see that the US has a very small production, less than 1%, and that around 70% is mined in Congo. The whole world is therefore highly dependent on Congo's cobalt mining. In terms of supply risk, this is a concern both globally and for the US, as Congo is politically unstable, and a reduction in mining production could halt the global supply chain. The bottom right figure shows the world cobalt refining by country. Although most cobalt ore is mined in Congo, they only have a very small percentage of the global refining capacity. Instead, we see that around 60% of the global refining capacity is in China, which is the dominant player. This could also pose a risk for the US, given that China is the US's main competitor and trade relations between the countries have been strained for the last years. An indicator showing just how vulnerable the US supply is can be seen in the yellow box. The US domestic production is only 4% compared to their imports. Given that the US has a very small domestic raw material production, looking at their stocks and reserves can also be important. From the two indicators shown, we see that the US consumption, compared to their total lithosphere reserves, is 14%. And comparing their consumption with their total stocks, we see that every year their stock is consumed more than 6 times. This means that if the import of raw cobalt stops, the US would consume their total stock in under 2 months. Given that the cobalt is a trace metal, limiting its availability and extraction rates, and that the US is extremely dependent on import, a high recycling rate becomes critical from a supply perspective. Currently, the OECD end-of-life recycling rate is just 32%, a figure that has been decreasing the last years. This is mostly due to the explosion of cobalt usage in rechargeable batteries, which are complex to recycle and therefore have a low recycling rate. Given what I just mentioned about the change in cobalt usage, we'll quickly look at some historical trends. In the left figure, the solid dark blue line shows the global consumption of cobalt, which has increased exponentially since the early 90s. In the figure to the right, the green bars shows the percentage of cobalt used in battery production. As you can see, this share is rapidly increasing and is predicted to do so in the coming years as well. Now let's take a quick look into the predicted future of cobalt. In the left figure, the blue line shows that the current exponential cobalt consumption is predicted to continue in the coming years. As cobalt is mined as a byproduct of copper and nickel, its extraction rate is limited. In the top right figure, we see that the current surplus of cobalt is predicted to turn into an increase in deficit in just a few years. But as mentioned, there is a large unused potential in cobalt refining. Comparing the amount of refined cobalt produced with the amount of cobalt mined, we see that 25% of all mined cobalt is never refined. To compare the global usage of cobalt, we can use the world map shown here. In the map, sizes of countries are distorted according to their cobalt consumption. Although it doesn't show the exact per capita consumption, it is still clear that the vast majority of cobalt is consumed in strong economies like those in North America, Europe, and East Asia. Meanwhile, in Africa, where most cobalt is mined, the consumption is very small. So from an intragenerational justice perspective, you could say that cobalt is consumed in richer countries, while poor countries are left with the local environmental problems that comes from mining activities. Another very important thing to note is the current human rights situation in Congo. Cobalt is often talked about as a conflict metal, since the income from mining in Congo is often used to finance local armed groups. There is also a problem with general corruption in the country and the high prevalence of poor working conditions and human rights abuses like child labor. Next, we'll focus on the cobalt from an environmental sustainability perspective, starting with the land use in mining and production. LCAs have shown that the land use is the category with the least impact in mining and production of cobalt, as can be seen in the figure, where the blue line shows the overall impact of producing 1 kilogram of refined cobalt. The most recent LCA we found, from 2019, shows that around 70% of land use can be attributed to mining activities, and that most of this is not due to the actual mines. Instead, around 50% of the total land use comes from storage of tailings. If we take a closer look at Congo, where most ore is mined, the picture becomes a little more complex. The mines in Congo are situated in biodiverse rainforests, which are not actively protected from exploitation. Instead, they have so far been protected by the political instability of the country, which limits the economic development, as well as poor infrastructure like lack of roads. But the copper and cobalt mines have become a part of a chain of activities that increase the forest exploitation. The mines are an economic drive in the country, leading to migration to forest areas where villages are settled. This creates a local demand for firewood and farmland, leading to deforestation. Therefore, the total land use is slightly higher than what can be attributed to the mines.
Let's move on to assimilation capacity of cobalt. We have an increasing stock of cobalt in society, as you can see on the graph here, and this is a lot due to the more extensive use of rechargeable batteries in society, as well as superalloys like aircraft engines. But we also have dissipative use that in this case mainly come from inks and pigments, but also other chemical processes. As you can see here, the global warming potential in kilograms CO2 equivalents per kilo for cobalt is quite low if you look at the scale going from lowest to highest impact here. And since cobalt is a metal mined in low quantities, it will not be especially high compared to other materials when multiplied with the total mass. The problem with cobalt mining, though, is that the environmental impact for nickel and copper also matter during cobalt mining. On this slide, we look at cumulative energy demand to the upper left, terrestrial acidification to the upper right, freshwater eutrophication to the lower left, and human toxicity to the lower right. In all of these cases, apart from cumulative energy demand, the impact for nickel and copper is actually higher than for cobalt, which shows that even if cobalt wouldn't have a large impact, the other metals that is mined together with it will affect the environmental impact from cobalt mining. So, what is the largest environmental impacts from mining and the cobalt extraction processes? It has shown to be eutrophication and global warming that is the highest impact categories. This is connected to blasting, which is a process where hot air is used to separate metal and slag, and the other reason is due to the electricity, which is driven by lignite or brown coal as it's often called. And the same thing here as I talked about on the previous slide. Copper and nickel is actually contributing to these impact categories more than cobalt does, as you can see for our calculated indicators. Especially when it comes to freshwater eutrophication, the difference is immense when comparing both the impact for copper and nickel with the impact for cobalt. We have also looked at different measured concentrations of cobalt in the environment, and on this slide you can see the values for cobalt in stream water near mines in the US, as well as the proposed Environmental Protection Agency benchmark. In our two indicators below, we have both compared the concentration in stream water far from mines with these numbers. As you can see, we have a quite wide interval, and this is because the measured concentrations came in intervals, so we decided to calculate both for the low and high ones. On this slide, we show pretty much the same thing, but for soils instead of waters. Also, here we have indicators for both the low and high measured values. The upper indicator shows the situation in the US and the lower indicator the situation in Congo. And as you can see, the concentration of cobalt in the soils near mines compared to distant from mines show to be higher in Congo. But what is the ecological effects from cobalt really? Cobalt is shown to be accumulating in plants and animals, but it is not proven to biomagnify up the food chain. It has also toxic and long-term effects on water organisms. When it comes to human health, particles that is inhaled could cause severe lung effects, which is mainly a problem for miners. High doses could also lead to other very undesirable effects, as for example vomiting and nausea.
Finally, we'll look back on some key parts of the presentation and what conclusions that can be drawn on the sustainability of production and use of cobalt. From the MFA, we could conclude that there are relatively high production losses to the environment, and that a relatively large portion of the mined cobalt is never refined. From a US perspective, cobalt has a high supply risk, as the country is largely dependent on imports. And from a global perspective, the scarcity of cobalt limits the extraction rate. Together, this shows that high recycling rates are critical to ensure a stable cobalt supply. This will be especially true for rechargeable batteries, which is the main drive for increased consumption. We also found that there is an unjust distribution in the use of cobalt. In terms of environmental sustainability, land use is the lowest impact category, and is mainly due to mining activities. But the mines in Congo also drive activity in rainforest areas, leading to increased deforestation. We also found that we have increasing stocks in society, and in the analysis of assimilation capacity, we found that eutrophication and global warming have the largest impacts, mostly due to blasting and electricity used in refining. But as a co-product, the emissions due to cobalt production is relatively low compared to the main metals, copper and nickel. Studies have also found that there are high concentrations of cobalt near mining areas, which could damage local ecosystems and humans. Lastly, we hope that you found the presentation interesting, and we want to thank you for listening.